Hi student friends, I am presenting my next series of videos on the topic application of partial differentiation, in which I am presenting videos on the following topic. Number 1, Jacobian. Second, maxima and minima of function of two variables. Third, Lagrange's method of undetermined multipliers. And the fourth, Taylor's and Maclaurin's theorem for function of two variables. First of all, I will discuss the first point, Jacobian. Its definition is if U and V are functions of two independent variables, x and y, then the determinant of derivative of u with respect to xy and first row dou u by dou x, dou u by dou y, and in second row derivative of v with respect to x and derivative of v with respect to y is called Jacobian of u v with respect to x and y, with respect to x, y, and denoted as it is denoted by capital J is equals to dou of uv divided by dou of xy, and that is equals to a determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. This is the definition of that Jacobian. Okay, we can extend it for function of three variables. Similarly, if u is a function of x, y, z, u is a function of x, y, z, v is another function of x, y, z, and w is third function of xy z, then J Jacobian is equals to dou of UVW divided by dou of x, y, z, and this is nothing but a determinant of third order, in which first row derivatives of u with respect to x, y, z, dou u by dou x, dou u by dou y, and dou u by dou z, then dou v by dou x, dou v by dou y, dou v by dou z, and third row derivatives of w with respect to x, y, z, dou w by dou x with respect to y, and derivative of w with respect to z. Therefore, this is the Jacobian when u and v are functions of two independent variables x and y, and if we have three variables u, v, w, which are the functions of three independent variables x, y, z, then determinant of third order is nothing but the Jacobian. Then we try to solve some examples to find. First example, if x is equals to r cos theta, and y is equals to r sin theta, then find the Jacobian, then find Jacobian of the given transformation. Here given x is equals to r cos theta, function of r and theta, two independent variable, y is equals to r sin theta, again function of two independent variable r and theta, then Jacobian, it is dou of xy divided by dou of r theta, and as per definition this is the determinant of in first row derivative of x with respect to r with respect to theta, then derivative of y with respect to r, and derivative of y with respect to theta, and this is equals to, we find all these four partial derivatives. Therefore, differentiating this with respect to r, cos theta is constant outside, and derivative of r with respect to r is 1. Therefore, that term is cos theta. Then differentiating same with respect to theta, this time r is constant, and derivative of cos theta is minus sin theta. Differentiating y with respect to r, we get sin theta, and differentiating this with respect to theta, r constant, derivative of sin is cos theta. Finding the value, this into this, it is r into cos theta, we get cos square theta, and minus, and this minus, it become plus, r sin into sin, we get sin square theta, and therefore we can take r common, it is sine square plus cos square theta. But sine square plus cos square theta is 1 and therefore it is r. The value of the Jacobian is r. If u is equals to x plus y plus z, uv is equals to y plus z, and uvw is equals to z, then find j, which is equals to dou of xyz divided by dou of uvw. Here we require to obtain Jacobian of xyz with respect to uvw. Means we must be known the values for xyz. Here xyz values are not given. Instead of that, some equations are given. Therefore, solving this equation for xyz, we get this. Therefore, from last we get the value of z as uvw. Okay. Put that value here to get the value of y. Therefore, we get y as uv. Transferring this z to left, we get minus z. It is uv minus z is uvw. From this 2, I can take uv common. The remaining is 1 minus w. Okay, that is the value for y, and x is equals to, from first we get the value of x as u minus y plus z value of y plus z, and that is u minus, the value of y plus z is uv, and therefore if we simplify it, from this I can take u common. It is 1 minus v. Therefore, we have obtained the values for x, y and z. Okay, and then Jacobian of xyz with respect to uvw is by definition a determinant of third order. First two derivatives of x with respect to uvw, then differentiating y with respect to uvw, differentiating z with respect to uvw, and this is equals to finding this all derivatives. Therefore, differentiating x with respect to u, this is constant term taking outside, and derivative of u with respect to u is 1. Therefore, we get 1 minus v as the derivative. Then differentiating this with respect to v, u is constant term, its derivative is 0. Derivative of this term with respect to v is minus u, and derivative of x with respect to w, as no term of w is there, its derivative is 0. Then differentiating y with respect to u, its derivative is v into 1 minus w. Differentiating with respect to v, constant term is u into 1 minus w. Into derivative of v is 1, means we get u into 1 minus w. And differentiation of this with respect to w, u constant, is derivative 0, and derivative of this term is minus uv. Then differentiating z with respect to u, we get vw. With respect to v, it is uw, and with respect to w, it is uv. Okay. Then simplifying it, finding the value, first term is 1 minus v, neglecting this row and this column and taking a determinant of this, that product is uv into u 1 minus w minus this product, minus and this minus, it become plus uv into uw. Okay. Then minus u and this minus, it become plus, and neglecting this row and this column, taking determinant of remaining 4. Therefore uv into this v into 1 minus w, and minus and that minus, it become plus uv into vw, uv into vw, and the third element is 0 into the determinant of neglecting this row and this column, determinant of this 4, 0 into anything else, we get 0. And then simplifying further, it is 1 minus v multiplied by, it is u square v minus u square vw and plus u square vw, okay, plus u into it is again u square v minus multiplication of this, it is uv square, then minus uv square w and plus u v square w. Okay. Therefore, if you simplify it further, this minus u square vw cancel with this u square vw. Here minus u v square w cancel with this u v square w, and therefore it is u square v minus u square v square and plus u square v square, and therefore it is equals to, if you simplify it, this get cancelled, we get the final value as u square v. This is the value for that Jacobian. final value or the value of the Jacobian is useful. If y1 is equals to x2 x3 by x1, x2 x3 by x1, y2 is equals to x1 x3 by x2, x1 x3 by x2, and y3 is equals to x1 x2 by x3, then find Jacobian of y1, y2, y3 with respect to x1, x2, x3, x1, x2 and x3. Okay. Here three variables y1, y2, y3, functions of three independent variables x1, x2, x3, and we require to find this Jacobian. Therefore, applying definition of Jacobian, Jacobian of y1, y2, y3 with respect to x1, x2, x3 is nothing but a determinant of differentiating y1 with respect to x1, x2, x3 in the first row, differentiating y2 with respect to x1, x2 and x3, differentiating y3 with respect to x1, with respect to x2 and with respect to x3, and it is equals to finding all these partial derivatives keeping other variables constant. Therefore, when we differentiate this with respect to x1, x2, x3 constant term, and derivative of 1 by x1 is minus 1 by x1 square. Therefore, that derivative becomes minus x2, x3 by x1 square. Then same way to differentiate with respect to x2. This time x3 and x1 are constant term. Therefore, x3 by x1 constant, and derivative of x2 is 1. Therefore, we get x3 by x1. Next, with respect to x3, x2 by x1 constant term, and into derivative of x3 is 1. And finding the remaining derivatives exactly on the same line. Differentiating this with respect to x1, we get x3 by x2. Differentiating this with respect to x2, minus 1 by x2 square is the derivative into this constant term. Therefore, it becomes minus x1, x3 by x2 square. With respect to x3, x1 by x2 is constant term. Then finding derivatives of y3 with respect to x1, x2 by x3 constant outside, derivative of x1 is 1, 1 into this we get same. Then with respect to x2, it is x1 by x3, and then differentiating with respect to x3, minus x1, x2 by x3 square. Okay, and then find the value, but as if you try to go directly, somewhat lengthy calculation. Therefore, we apply the properties of derivative to simplify it. Therefore, I can take x1 square common from the first row, x2 square common from the second row and x3 square common from the third row. Therefore, performing it, 1 by x1 square I am taking common. If you take this common, the remaining is minus x2 x3. If we take 1 by x1 square common, here it is x1 x3 remains. And if we take x1 square common from this, x2 x1 or x1 x2 remains. If we are taking x2 square common from the denominator, in the first we have the term x2 x3. Here it is minus x1 x3, and here it is x1 x2. If we take x3 square common from this denominator, the remaining terms are x2 x3, then x1 x3, and here it is minus x1 x2. From first I am taking 1 by x1 square common. From second I have taken 1 by x2 square common, and from third I have taken one more step. I will take column wise common. From first column I can take x2 x3 common. From second column I can take x1 x3 common, and from third I can take x1 x2 common, and divided by this x1 square x2 square x3 square. And after taking this term as a common, the remaining is here minus 1 1 1. Here it is 1 minus 1 1 1 1 minus 1. X1 into x1, x1 square cancel with this x1 square, x2 square cancel with this x2 square, and x3 square cancel with this x3 square. And therefore, this is the remaining, and its value is minus 1 into product of this 1 minus 1. Okay, then the second term is minus 1, neglecting this row and this column. 1 into minus 1 and minus 1. Okay, and plus 1, neglecting this row and this column. Determinant of this remaining 1 into 1 1, minus, and that minus it becomes plus 1. And therefore, if you simplify it, 1 minus 1, it is 0 into anything 0. Minus 2 into minus 1, we get plus 2. And this 1 plus 1, 2, 2 into 1, we get 2. And therefore, its value is 4. That is the value for this third Jacobian. Like this, we can determine the Jacobian for the given transformation, whether it is a function of 2 variables or whether it is a function of 3 variables. In second part, I will discuss the properties for Jacobian. That property is j into j dash is equals to 1. The problems on this property I will discuss in the second part of this video.